So far we have studied the rotation of a molecule, pure rotation of a molecule, and then pure vibration of a molecule, and then electronic structure of a molecule. Now, in electronic structure basically vibration as well as rotation are involved, there comes together, right. So, this is the overall the basic fundamental study of the molecular physics. So, now as you know, this atomic and molecular physics is basically based on the spectroscopy. So, this to study the structure, atomic structure and molecular structure. So, one has to use spectrometer, spectroscopy. Okay. So, that is why there are various kind of atomic spectroscopy and molecular spectroscopy. Okay. So, in different name. Okay. So, today I will discuss about one spectroscopy that is basically called, it is very useful for studying the rotation and vibration of the molecules. So, that spectroscopy is basically called this Raman spectroscopy. Raman spectroscopy. Okay. So, this spectroscopy based on the Raman effect. So, you know the history of the discovery of the Raman effect. Raman effect. Okay. So, what is that? What is Raman effect? So, it was discovered in 1928. 1928, I think that is on that date, 28th February, most probably, yes, 28th February it was discovered. In 1928, it is 28th February, it was discovered by Raman, C.V. Raman. It was discovered by C.V. Raman in an research institute, that is called this IACS Kolkata, in IACS Kolkata. That time it was Calcutta, IACS Calcutta. Okay. So, IACS this is basically Indian Association for the Cultivation of Science. Indian Association for the Cultivation of Science, I do not know whether you have seen this institute in Kolkata, it is in Jadavpur now, but earlier when C.V. Raman works for this for his research. So, that institute was in Bowbazar, it is in Kolkata, now it is shifted to Jadavpur, but its name is same, IACS, Indian Association for the Cultivation of Science. Indian Association for the Cultivation for the cultivation of science. Okay. Okay. It is just the opposite side of Jadavpur University. So, this C.V. Raman, he was basically he was general accountant. In his posting was in Kolkata, because after MSc, I think he C.V. Raman, he did his BSc from Presidency College, Madras. When he was 16 years old, he completed his BSc. He stood first in the class and he was the gold medalist. Okay. And I think when he was 16 years old, BSc, and I think when he was 18 years old, he completed the MSc from Presidency College, Madras. And then for further study, one has to go to London, but he was somehow, his health was not good. So, that is why he was not able to go to London for further study. So, then he chose the job, this I think this very prestigious job, financial department of British, and this is called accountant general, and his posting was in Kolkata. So, he used to go to office by tram, and when he was going and coming back, so one day he saw a research institute. Its name is Indian Association for the Cultivation of Science in Bowbazar, and then he got down from the tram and he went there, and he found his suitable place to do some research, and he started research work after office hour. And he, I think he did lot of research work, but this the ultimate this is the major success of his research, this discovery of Raman effect, and in 1928, and immediately he got the Nobel Prize after 2 years of this discovery. So, 1930 he got the Nobel Prize. So, this is the first Nobel Prize got by Indian. No, I think Rabindranath Tagore, before that Rabindranath Tagore, but in science he was the probably first. This is the first Nobel Prize in physics one Indian got this C.V. Raman, but before that, in literature I think Rabindranath Tagore got. So, Nobel Prize in 1930, Nobel Prize. Okay. So, that was the brief history of the discovery of the Raman effect, but what is that effect? What is that Raman effect? So, actually in general, is the scattering of light, is the Raman effect basically is the scattering of light from. So, if light or electromagnetic radiation, okay, it may be visible light or this other electromagnetic radiation, when it falls on a sample. Okay. Now, this light scattered from this matter, from this substance, from this object, right. Okay. So, now there are two types of scattering. So, this is in general scattering. So, there are two types of scattering, one is called elastic scattering, another is called inelastic scattering. Elastic scattering and another is called inelastic scattering. So, what is elastic scattering? So, this light or incident radiation falls on the object and this incident light or radiation scattered by this object and this scattered light in all directions. If the wavelength or frequency, say incident radiation, its frequency say nu I or wavelength lambda I or wave number whatever. Okay. If this and then scattered one, this if I write nu s or lambda s. Okay. So, if nu I equal to nu s incident one and then scattered wavelength of the scattered light, if it is same, then it is called elastic scattering. If it is not same, nu I is not equal to nu s, okay, then it is called inelastic scattering. Okay. So, Raman scattering was basically it is inelastic scattering. Raman scattering was inelastic scattering. So, Raman scattering was inelastic scattering. Raman scattering is basically inelastic scattering. So, what Raman found that when this sunlight or light from I think from mercury source, okay, when he put on the sample of molecules okay. So, then this incident light is scattered by these molecules, by this sample is of molecules, okay, scattered by these molecules. Okay. So, then he found that most of the light have the frequency of incident wavelength or incident frequency, okay. But there are some scattered light, very weak light, means scattering strength is very small. So, he got basically in spectrometer when he checked the wavelength of the scattered light. So, he found basically this one strong lines having the frequency of incident light, okay, or radiation, and then these two additional lines he saw, but it is very weak lines. So, one is higher than the original frequency or wavelength, another one the lower frequency or wavelength, and their separation, separation is basically same. Okay. The separation is basically same, and that is what I think. Yes. So, this frequency, that frequency difference, was basically, say if I write del nu, okay. So, he found that two other lines of frequencies basically nu I plus minus delta nu, okay. plus minus delta nu. So, frequency of this one is so frequency of this one nu I minus delta nu, and frequency of the other one here nu I plus delta nu, okay, plus delta nu. Okay. But intensity of these two lines are very weak, and these two lines he called these lines, one is Stokes and anti-Stokes lines, Stokes and anti-Stokes line. So, this line at lower frequency is called Stokes lines, S-T-O-K-E-S, Stokes lines, Stokes line, and this called anti-Stokes line. Okay, Stokes line and anti-Stokes line. Okay. And this original one, this the it's called Rayleigh scattering. This because it's called Rayleigh scattering. Or Rayleigh scattering. So, one can tell this Rayleigh line. Okay. So, original the same frequency and highly intense, other two is very weak, and this frequency of these two is plus minus del nu, original plus minus del nu. So, this lower frequency one, this line is called Stokes lines, and other line another is anti-Stokes. So, now Raman basically, earlier it was not known, these two lines Stokes lines and anti-Stokes line, it was so weak and it was very difficult to see that one. And problem was earlier this all experiment was done using the sunlight. Okay. That was the most intense light. Later on this some mercury light, arc light, etc. this was came up, and Raman was able to see these two lines. If you see scattering is very weak. So, if you can increase the intensity of the incident light, then there will be higher probability to get this higher probability to get this this scattering. What I mean this, so then this you will get. So, scattering strength, it is defined, it defined basically per unit per unit per one, say here scattering center, and per one this what I call per one ray, you can see tail of it is particle, per one particle, incident particle, okay. That is the scattering strength. Now, strength will not increase, but you see this if you can increase this one, this total cross section, scattering cross section, you see it will be. So, whatever the intensity will get there, so that depends the scattering cross section, scattering strength, and also intensity will depend on the number of these incident photons, as well as the number of the molecules, say here in this case number of the scattering center. Okay. So, if you increase either the number of scattering center or the number of incident particle or incident photons, so it is possible to get the comparatively higher intensity which can be detectable. Okay. So, that is why Raman was able to see this one, because he used this lens, okay, to focus the to focus the light and put the focused line on the sample. Okay. So, that was the, I think, because of that he used this higher bigger diameter lens, and he was able to condense or converge the light, all light on the sample. So, thus incident intensity of light was high, and because of that he was able to see this very weak lines. Okay. If this intensity is not high enough, it is so faint, it is people will overlook that one. Anyway, so that was the that's what observed by the Raman, and this is called Raman effect. Okay. And he explained what is the from where these extra two lines are coming. From where these two extra lines are coming, Stokes lines and anti-Stokes lines, from where it is coming. So, that is what he experimentally observed, and he explained the origin of these two lines. And he explained that this is coming from the molecule, and it is due to the rotation and vibration of the molecules. These Stokes and anti-Stokes lines are coming. So, origin of the Stokes and anti-Stokes lines is basically due to the vibration and rotation of the molecules. Okay. So, Raman spectroscopy is thus it is related with the molecular spectroscopy. So, this spectroscopy is now it is a very useful research tool instrument to study the different kind of molecules, to study the vibrational and rotational structure of the molecules, and some other in case of solid etc. Now, it has vast application, but discover wise it was it was observed due to the molecular vibration and rotation, and now this application of it is expanded in different direction. Main reason is that this now laser light is available. Laser light it is focused and it has tremendous intensity, and it is monochromatic. Okay. Monochromatic wavelength means it has single wavelength. So, now Raman spectroscopy is very simple one, and it is used this it is used means this Raman spectroscopy is, I think, is all over the world. It's people have this spectroscopy or spectrometer. So, let us see now that how Raman explained this origin of the Stokes and anti-Stokes lines. Now, you see, so now one has to differentiate. You see this, it is related with the rotation and the vibration, that is fine, and also we have seen this just pure rotation and pure vibration of the molecules. What happens that we have seen when they are also involved, they come together with the electronic transition. Okay. So, this basically here one that I will tell you, in this case the difference is that this you remember when I was telling this absorption spectroscopy. So, there absorption spectroscopy. So, there what we have seen this so this pure this vibrational spectra, and that is the that we have seen these molecules, it absorbs the some wavelength, and that wavelength is because of the is related with the vibration of the molecules, right. So, emission spectroscopy, that is other way. If you excite the molecules and then it will emit light. Okay. Now, if you study that light emitted from these molecules, so now that is the emission spectra. Okay. So, here in this case incident light. So, geometry is the incident light, focused light, or nowadays laser light is used. Laser light will fall on your sample. Now, sample is basically say simply is molecule. Now, this now the molecule, now the incident light will be scattered from this sample, from these molecules. Okay. And this its geometry is that now this scattered light, this studied in spectrometer, this scattered light at 90 degree. So, this is the incident direction of light. Now, at 90 degree the spectrometer is set and this scattered light is collected at 90 degree and put in spectrometer. Now, spectrometer is standard, you know this, one has to use grating, that collimator will be there, telescope will be there, and this prism table will be there. So, prism table, spectrometer table. So, on table this in this case generally now grating is used. Now, you understand that why grating is used, because what are the wavelengths are coming that I want to see, that I want to measure, right. What are the wavelengths are coming that I want to measure. So, to separate that wavelength, one has to use either prism nor this grating. So, to separate, to keep spatial separation, to make spatial separation of the wavelength. Okay. So, that is basically dispersion. Grating and prism both have dispersive power. So, to disperse the wavelength in space, so that is why there is a now you will measure one has to use the detector photomultiplier tube if it is visible light, and then you will measure the intensity of light of the scattered light is coming through the prism or the grating. So, what are the, so you will measure the intensity at different places, means different places you will have different wavelength, right. So, that wavelength how it is spatially dispersed. So, that is related with the prism parameter or the grating element, okay, grating parameter. So, thus you will measure the intensity of different wavelength of the scattered. So, then when you will measure, then it is found that this original at this wavelength things are coming, most of the scattered light are at this wavelength, and there are other two wavelength also it is observed, or frequency also is observed. So, what are the intensity? So, that is the Raman just sketch of the Raman spectrometer. Okay. It is used. So, you will get this kind of this spectrum which will have this three wavelength. Okay. And you may have the more wavelength, but that depends on, that will depends on the, because the del nu, as I told, this del nu how much it is, it will have the value. So, that depends on the molecule. Okay. So, del nu will be different for different molecule, and so for other condition bonding etc., when molecules are in solid form or liquid form whatever. So, these are the so del nu will be different, and del nu is related with the molecules, molecular vibration and rotation. Okay. So, measuring this separation, okay, now one can relate with the structure of the molecules. So, thus this is the research matter, and this not only this 1 2 lines, you can have many lines, that because of many factors in this sample, it may not be the single same type of molecule, there may be existence of other type of molecules or some other factors, but for simplicity this one kind of molecule, simple molecule, diatomic molecule. In this case this you will get only these 2 lines, okay, and additional in addition with this original frequency. Okay. So, so this is the geometry, Raman spectroscopy, that is the spectrometer, the geometry, and these the lines was observed, and this I will show you this this is related with the rotation and vibration of the molecules. So, I think this will I will discuss in next class. So, I will stop here. Thank you.